We ended lesson 19 with these sketches of force curves taken with high and low spring constants, but I didn't emphasize that these curves are taken as a function of scanner position. It turns out that that's not so convenient when we try to fit models to these data, as we'll see throughout this lesson, in which we address how force curves are processed. In order to talk about how force curves are processed, we need to make a little model ourselves. I'm going to represent the cantilever and the tip-sample interaction as two springs in series. The notation is a little bit different now. Instead of using K perpendicular, I'm going to use KC. And for the tip-sample interaction, I'm going to use Ki for its spring constant. The I subscript is a reminder that both the tip and the sample are involved in the stiffness of that system. I put an arrow through that spring representing the tip-sample interaction. That is a reminder that whereas the spring constant of the cantilever is fixed once you mount one in your AFM, the spring constant of the interaction can change. It's variable, and it can be either less than or greater than 0. Okay. Now I've added a z-axis scale with indicators for the holder, the cantilever, and the sample. And if you look at that scale, I think you'll agree that the distance h minus s can also be written as h minus c plus c minus s. Okay? So these distances, well, if you imagine compressing the distance h minus s, that's the whole system, the system of the cantilever and the tip-sample interaction. That could also be written as the total force divided by the total spring constant, where the total spring constant is some combination of Kc and Ki. H minus c, that's the cantilever part. So we could write that as F sub c over K sub c. And c minus s, that is the compression or extension of the tip-sample interaction. So we can write that as Fi over Ki. So just making use of the linearity between force and deflection or compression or extension of springs. Now, something really cool. If you remember Newton's third law, that says for every quote-unquote action force, there's a quote-unquote reaction force. You apply this to the system, and what you find is that the total force is the same magnitude as the force of the cantilever, and that's the same magnitude of the force of the spring. So this equation becomes 1 over K total is equal to 1 over the spring constant of the cantilever plus 1 over the spring constant of the interaction. I've repeated this equation. Let's invert it now and see what K total looks like as opposed to the inverse of K total. So here I'm taking the inverse of K total to get K total. And now you see a mess on the denominator, but what you can do is you can multiply this expression by 1. And here I have a very fancy form for 1. KCKI over KCKI, that is still 1, even though it doesn't look like initially. So the numerator we get KCKI, and in the denominator we get the sum of Kc and Ki. So there's our expression for the total system stiffness when you're compressing both springs, as you do as you collect raw force curve data. Note something interesting here. I'm repeating this again. We're going to consider the following case. We'll consider the case of Kc being much less than Ki. What you can do then is say in the denominator, oh, let me just ignore that term. And then if you look at the numerator and the denominator, you can cancel the Ki's out such that K total in the limit of a weak cantilever just goes to the cantilever stiffness. Returning now to our raw force curves as a function of scanner position, what we've learned is that the slope is equal to the total system stiffness, and in the case of a weak cantilever, that slope becomes the stiffness of the cantilever itself. This situation is not good. What we would like are data that reveal the interaction between the tip and the sample. We don't care about the cantilever. We want to know as much as we can about the sample. So what do? We tell our computer to take advantage of the equation that I wrote a few slides ago, saying the distance between the cantilever holder and the sample is equal to the sum of the cantilever compression or extension plus the distance between the cantilever and the sample. In fact, let's write this more compactly now. Sample holder, cantilever holder minus sample surface is equal to the magnitude of the cantilever deflection plus delta, where delta is either the separation between the tip and the sample or the penetration or indentation of the tip into the sample. It's delta that's the key to this. So solving this, that would be h minus d minus s. Okay, why do we want delta? Because delta is equal to force over Ki. So if we can replot our raw data as a function of delta, then what we'll find is that the spring constant associated with the interface, the tip-sample interaction, it will be the slope of a force delta curve. So these two process curves I'm about to sketch in 2 steps have delta on the x-axis, the separation or penetration depth. What you tell the computer is, computer, take this point, it's at a certain force and a certain z, and we're using the notation h here, and replot that, taking into account our expression for delta, as we're going to use as an offset. D is the deflection. Well, you can get the deflection because, of course, you know that that is equal to the force of the spring constant of the cantilever. That's inherent right in the curve. So processing for delta, we would take that point and we'd use the same force, but now delta, that's a smaller number than h, so that point might come out right about there. That I tried to make it the same height but smaller distance along the x-axis. So you tell the computer to do that for all the points on your raw curve, and essentially what happens is it looks like this, i.e. it becomes a little bit squished. But the good thing is, the slope here is now ki. There's one more step, and that is we should shift the curve back and forth such that the curve crosses the y-axis at a point that represents the sample surface. So we're going to use fs as an offset in the red boxed equation. And I like to think of contact beginning here at this inflection point, but that can be difficult to identify. And you're pretty close if you take contact as the minimum of the approach curve, just for starters, before you get into too much detail about the contact mechanics. So this becomes a curve that looks like this. Okay, so I've tried to keep the same shape as the one immediately above it, and all I've done is shifted it to the left along the x-axis, which is now the separation or penetration depth. Here on the left, I've redrawn the force as a function of separation or indentation depth curve for the stiff cantilever, the one we've been talking about, and hurrah! The slope is the spring constant for the tip-sample interaction. What would that curve for the weak cantilever look like once it's processed? Well, remember there's a long straight line in it when the cantilever is in contact with the sample. What that becomes is just a vertical line along the y-axis, and the jumps look like this. This one for the approach, this one for the retraction, with the evident hysteresis there. Now, you might wonder how to interpret this. Well, you've got a weak cantilever. That means as you compress the system, it's so weak you cannot detect any compression of the sample. That's why we've got a vertical line along the y-axis, the force axis, meaning that as we compress and give more force to the system, we're not indenting. Note that that can also happen with stiffer cantilevers. On the left here, I've drawn this such that at the higher loads, we've got also an infinite slope. Basically, infinite meaning infinite with respect to the particular cantilever that you're using. Okay, again, you can compress so much that the tip-sample interaction becomes progressively stronger, and at some point it overwhelms the stiffness of the cantilever. That's what those infinite slopes mean. Here's my summary slide showing raw and processed force curve data for stiff and weak cantilevers. The important thing to remember from this lesson is that the separation of the tip in the sample, or the penetration of the tip into the sample, is equal to the scatter height, or alternatively the position of the cantilever holder, minus the deflection of the cantilever, minus the sample surface height that we use as an offset in order to give the delta equals 0 position meaning as contact.